Grab your coffee. No, don't grab your coffee, then come here. That'd be tacky.
You didn't mention it's given by the most modest speaker.
That's right, the most modest and humble speaker in the history of supercomputing. How long am I supposed to talk? 15 minutes? But I've got like 45 minutes of great material here, then I better get started. So I have no idea what sort of background you all have in OpenMP, and since I only have 15 minutes, I'm going to plunge onward, but make this interactive. I'm going to have to judge from your body language when to go slow and when to go fast. So I'm talking about the OpenMP Common Core, which is a quest I've been on for several years now, to the irritation of some of my colleagues, because I'm focusing on a look back. Let's not look forward, let's look backwards. So when we look at the beginning of OpenMP, this is a plot of the number of pages in the spec over time. Now, we removed the front matter, we removed indices, examples, appendices. This is the part of the spec that defines the language. And as you can see, we started out with separate specs for C and for Fortran, and we started out around 40 pages. And after several implementations, we got up to around 60 pages. This is good. This is good. And it all fit in, and I went back to one of the oldest slides I could find on my laptop. I've been teaching OpenMP since 1997. So I've been teaching this stuff a long time. This is from 2003, our introductory slide to OpenMP. And all I want to emphasize is we stated the whole goal of this thing was to make it easy to create multi-threaded programming. What people have to multi-threaded programs. What people have to remember is the goal was simplicity. That's what motivated us. That's what we were out to do. So over time, we merged the Fortran and C specs, and I have to just say, oh, this died down a little bit. I have to say that the OpenMP 2.5 spec is the one that we could really be proud of. The ones before that, we were all amateurs, and it showed. 2.5 is a thing of beauty. And I'm not saying that arrogantly, that it's because of me. No, it's just we kind of figured it out, and we became masters at spec writing. But think about it. That was 1, 2, 3, 4, 5. It took us until the 6th one to really get it right. Now, what these all focused on was multi-threading, and mostly with parallel loops. And this was the hardware model. Now, I could go on through this whole stack, but basically, we assumed you had a symmetric multiprocessor system. Now, we knew better. We knew in the, the early 2000s that most systems are non-uniform, but we wanted to keep the system simple and figured that's a sacrifice we'll make. We'll just keep it SMP. We keep it really simple. As we matched on, we added tasks. How many of you have used an OpenMP task? Okay. They're awesome, aren't they? Aren't they wonderful? Anyway, we added tasks. We added SIMD constructs. Now, this is very important in OpenMP 3.1 in 2012 or so, because the hardware model changed. Now, all of a sudden, we didn't just have SMP. We had explicit vector units that we hung off of each one of those cores. So that added new hardware features to the model. Then we added NUMA constructs and target constructs, which made this radical change to the hardware model. All right, so now you could program a GPU from OpenMP. How many have done that? You have. Whoa, you're a real ringer. Okay, okay. Yeah, I've been teaching programming your GPU with OpenMP for several years now. It's fun. It's rewarding. It's really cool because we love GPUs. And I work for Intel, and I can proudly say I love GPUs. So at any rate, then we came out with the 5.0 spec, and you can see the trend here. We went from 40 pages to over 600 pages. I think we're getting a little complex. I think things are getting a little out of, well, I'm going to say out of control, but I want to be clear. And the reason I like to do this build-up, everything we've added was for a very good reason. The hardware changed, we changed. The algorithms people wanted to use, they wanted irregular parallelism, we added tasks. People realized, my hardware is NUMA, I need to start programming to it. So I am not criticizing the content that went into that 600 pages of spec. All I'm saying is we've lost sight of that original goal of simplicity. And I think we have to get back to it. I think we've made OpenMP a big, scary thing. Want to hold up the spec book over there? Yeah. That's the spec. Yeah, that's right. I haven't even read that whole thing. I mean, just, oh man. So I think the initial impression people now have when they come up to OpenMP is, this is too complicated. I'm just going to write Python. So I want to change that. I want to return to our roots and change how we present OpenMP. So we present that simple core and then build up from there. So, oh, and this asks the question, though, of, well, how do people actually use OpenMP? And they need to understand how people most commonly use OpenMP. So since I don't have a lot of time, I just want to say, I'm going to show several versions of the Pi program. I'm going to compute the area under the curve, and this is the simple code. And I hope you don't mind that it's in C. I know God programmed in Fortran 77, but I'm not God. I'm male, so I can't be God. So I have this in C. And so I think the most fundamental way people use it is this thing we call the SPMD program, the SPMD pattern. You create a team of threads with that parallel. You call your thread ID. You pick up how many threads. You use that to split up the iterations. And I can do a huge amount of programming this way. The advantage of this style of programming is it's very nice when you want to take advantage of the NUMA features of a system. So it's a really handy way to program. So that's one way people use it. So I call that like the fundamental building blocks of multi-threading. Parallel, get set thread number, get thread number. Oh, there's a typo there. Any rate. Then the other way people use OpenMP, oh, I'm sorry. What about Fortran? Yeah. Fortran programmers can't put declarations inside an executable unit of code. So you have to have these clauses for managing the data environment. So there's a cluster of constructs that just have to be there for Fortran users. Shared, private, first private, default none. And we use them in C too. It's just, in C you can actually adopt a style where you don't use these very often, but in Fortran you have no choice. So now we go to the way that perhaps most people think of OpenMP, and that is, oh gosh, I have to memorize my slides better. Okay, if you have threads, you have to put order constraints among the concurrent threads, that synchronization construct. And the ones that people use again and again in OpenMP are critical and barrier. So that's the next block, synchronization in the Common Core. Now we get to where I thought we were going to go next. To many people, and many of my friends at Intel, this is where they start. I don't. But they start with that, you put a pragma OMP parallel 4 and a reduction if you need it, and then OpenMP comes a way to split up loops. And this is a fine way to use OpenMP. I'm not criticizing it. It's just I like people to understand threads first, so I don't start there. So that's my next cluster. See? We're building the Common Core up. It's not that hard. Then, of course, you need tasks. Oh, I love tasks. Standard pattern of using tasks I'm showing here is divide and conquer. I have a single thread that starts things off, and then I recursively split my job down and put it back together. I would love to get a whole talk on tasks, but he's only giving me 15 minutes, and I'm through most of that already. So that's my next cluster of instructions for the Common Core. And then there's a few that I just couldn't describe anywhere else. No wait, the schedule clause is on 4. So that's the Common Core. It's an elegant API from a more civilized age. So it's really awesome. And I think for you experienced programmers who've been using OpenMP a long time, you've mastered the pieces of it you're going to use. That's great. The key thing about the Common Core is going to the effort to identify what it is that people need just to get started with serious application programming. And I submit that these constructs here are, for probably 95, 98% of OpenMP programmers, all they will ever use. So we should teach it that way. We should start with the Common Core, and only after you've mastered the Common Core, move on. And in case you're going, gee, I like that idea, I would like to start learning the Common Core, or I'm an experienced programmer, I should start teaching the Common Core, we've written a book, and she's holding it up over there. You could actually walk over and hold it in your hands. Cuddle it gently. It's a nice book. At any rate, I'm really proud of this book. It's a book that's needed to be written for a long time. And it's really a book about how to learn OpenMP, how to master OpenMP, and it breaks it down into these very logical, example-driven presentation of the Common Core. So it's a great book. It also has, I might mention, a discussion of the memory model, which as far as I can tell is not written down anywhere else in the universe. So even for more advanced programmers, the memory model chapter in the third part of that book is a must read even if you're more advanced. So go out and buy my book, okay? Or better yet, you might be able to win a copy. You just go and sign up with my lovely assistant over there, and you might be able to win a copy of the Common Core book. Or I just went to the MIT Press booth, and they have a few more copies on sale. And remember, if you buy them here, you get a 30% discount. So, and since you want to own the book anyway, you're going to save money. So that's all. I hope I hit my time limit okay. All right, that's good, that's good. And I don't have to go anywhere immediately after this, so I can get off camera and then answer any questions either about the Common Core or the future of OpenMP or anything about OpenMP or SYCL or HPF or Julia or I don't know, any HPC topic. Thank you.